Hi everyone, here's Simone from the studio. One new video. This time I want to share with you a creation of mine. This is a custom operator I've encoded mostly with Claude, and the name is CloudPop. This guy. Now I press 1 and you can see some instances of the CloudPop doing stuff. Like simulating the formable body with some points and a sort of rope in a cage, which is giving this kind of wormy spaghetti situation. A self-colliding cloth, which is the basic of a constraint solver, basically. And yeah, some points that they fall down, they act as more or less rigid body. So, yeah, they bouncing points. And then a kind of complex scene, which is more or less working as reality, with some deformable body, a cloth, and a static object that is acting as collider. As you can see, it's not super precise, but it can be used for some basic animation. So all the spheres are deformable body, and the cloth is a cloth, and the torus is a static object which can be moved, and you see is acting against those balls, pressing them. It's a kind of tricky result, and we are not even using volumes here because we have a cloth. So the solver has some limitation. But anyway, it's a complex scene that I like. So to showcase also what can be done, what cannot be done. But okay. So all those things are running real time in different instances of the CloudPop, and yeah, I'm keeping 60, and they are like stupidly fast to simulate. So the rope, it's more or less everything in the GPU. I'm still getting the concept behind pop, how to get them only with from the GPU. You still have some CPU here. I mean, the rope is less than half a millisecond CPU and a millisecond GPU. I have a 4090. No. You can run it. Another limitation that will be in the free version is that you can use 5,000 points. That's it, no more. So if I type 5,000 here, okay. Since 0 is a number, you won't get the animation. But if you, so this is the maximum of the point that you can use. It's already enough, I guess. There will be a pro version soon in my Patreon, but for now, just enjoy this free. And then the pro version will have some other feature, like welding stuff together. You can throw more points. You can have both soft body and something which is not 3D, because the grid is not 3D, you see. So, and also the static mesh, it can be static or they can act as a rigid body. This should be in the pro version. It's not ready now, I'm not happy, so just enjoy the free for now. And the free, it's free, okay? Just to tell you, this project is costing me like more or less 600 euros. I won't show you like the bill right now. It's like I pay more or less 150 euro per month with Claude, and my experience plus Claude writing the right code. We managed to achieve something which is fast, very, very fast. The sphere is stupidly fast. The complex scene is, I don't know, it's 4 milliseconds, but you have a lot of stuff happening. Okay. All this to tell you that a tiny contribution from my Patreon will be more than welcome. Okay, so how does these things work? As an example, now we go through them. Let me bring this here, and then we start with the rope. Okay, this guy. This guy is the first one, and it's a simple way to show you that what we are calculating are constraints. So this solver is one loop. You need to, before to put something inside, to think about what you're doing. So you cannot penetrate physical object. Material is not interpenetrating itself for whatever reason. Okay, so you need to leave space. Space for what? For constraints. Okay, a constraint is something which is or stopping you, stopping the movement, so it costs 100% constraint you, or in this case is something that it's trying to keep stuff together. Okay, so this is the rules. The rule, I mean, there is one. This object is doing this. It's kind of fast of doing that. Analyzing the scene, I wanted to build something which is ideally an operator. So you don't have to follow a pipe to achieve a result, which should be direct. You pipe something inside and the behavior you get is more or less what is supposed to be in reality. So here we are dropping a rope of point, and the rope of point, let's make it very slow. Okay, now it's very slow. It changes the behavior if you slow down this thingy. Okay, just to show you. Okay, now, pardon. Now things are exploding because of the constraint I was telling you. Okay, but then we keep everything inside of a cage. It doesn't really matter much. So we are putting this guy inside of a spherical cage. So this operator has two pre-built colliders, which are the floor and the spherical cage. We are now using the spherical cage, which can also now is like spinning. I put y as the axis of spin here, but you can also throw the velocity in other direction. So now you will see. Then we want to put some friction, so the particle will actually start to have a grip in the sphere which is moving. And yeah, maybe we can also spin it tiny faster. Exactly. So now you see I am like spinning a bit more on the Z and on the X and on the Z axis. So to achieve this motion, I should put a visualizer, but yeah, whatever. And now you see they are spinning, so it's a one big rope inside of a cage. And if we decrease the higher object collision, we don't need actually, because then there are not other objects. Yeah, it's one object here. Okay, all the points are connected and belong to one object, so it's one object. And we have two things running basically here, more than that affect the behavior later, but it's what is actually doing the math is easy. Okay, so each point of this line, I don't know if you can see it here, every point of this line, okay, there are a lot, okay, it's one after the other. Okay, so when I press in the cloth pop in it, simulation it, it's now connected to the keyboard one on my test tool. Okay, I am resetting. While it is resetting, also throwing a tiny error, you don't care much. It's for the CUDA sync. But it's actually taking every one of those points and say how far I am from my neighbor, basically. And based on how much you are the distance of the neighbor of the point we are processing all of them in parallel, we have a condition, we have a sort of collision radius. So the collision radius is how much they collide and how far is the point that I need to push away from me, how far I need to push away the other point. So if I now reduce this to something else. You will see also in the 3D thingy that the balls start to have the sphere start to become more one. That they goes one to the other. Okay, so if I put 0.5, it does this. If you increase it until a certain amount, we start to have this. So maybe we can increase the radius of the sphere. Okay. Okay, you get the point. So this is one collider. You can even throw another collider, which is a floor. Oh, you get this. They work both together. The floor, I mean, you can deactivate the other sphere and then leave the rope going around in space like this. Which is also nice. It flies away. Okay, fair enough. Let's put everything together. Yeah, okay. So this is the example of the rope. When I press one and my mouse is over this, it goes away from the perspective view. This is where I need to sometimes move. Clove. Okay, then a clove pop can do clove. Nice. So we take a grid. So we take a grid, and the grid we do a tiny trick. Okay. Since we're speaking about a computer which is trying to simulate reality, okay, we have to take in consideration the reality. Okay. So a piece of paper, for example, or the particle, the molecules that are composing this piece of paper, they also have neighbors. Okay, so now we want to simulate 4,000 points. It's okay. But nothing is perfectly flat in reality. Okay, so when you take a piece of paper or better a cloth, all the molecules they do not are flat. Perfectly flat is very difficult to achieve. Okay? So this is why I'm throwing some noise here. Okay, and then I tell you also a trick. You see where is this loop? Where is starting this grid is starting from 0 and going to the right, meaning all this grid is in the positive. We have plus here and plus here, plus in X and plus in Y. Nice. This is very useful if you want to throw stuff, for example, throw a noise and make like the point that goes up less affected from this noise. How you do this? Basically, you multiply the noise for the Y, okay? And you get this. And then you can just rotate it and you get this kind of grid. Okay, it's not perfectly flat now, but it pretends to be flat at the upper part. Like I'm sure we are actually pre-accelerating some points by moving them. Okay. Making like pre-stretching a bit the cloth. Then you throw it inside cloth pop and you leave the cloth pop animated. Okay. Cloth pop is very sensitive. Okay, it's a good guy, but you have to treat him correctly and you have to follow this rule again. This is one rule. You have to give space to constraints. That's it. This is why this grid is not small. Right? You have 40,000 points. And at the end, we are starting with this, which is a bit stretched on the Y, on the X, but at the end, I am pumping it here for sure. Yeah, like 3 times at least. Why is this always moving? Because we are always solving the constraints. Okay, that in this case, I am inputting a quad mesh because it gives me better normals at the end. but here I can actually show you the real. Okay, so those are the. So if I change these to alternate triangles, basically each part of the cloth now have a constraint, and this is what is actually calculating the distance between every line you see in this grid is actually the constraint which is built inside close pop when you input a geometry or you restart the animation. Actually, if it's already built then the topology doesn't change it. It's not calculating it. It's anyway very fast. Okay, so for the grid, the rules want that you drop code. Why? Because they give better normals at the end and they behave better. She is nice here. Okay, clove pop is also taking care of the normal calculation. In output, there is a pattern message. Yeah, you will have this turned on, so it's encouraging you to support my pro version if you want. But yeah, you can also compute or not the normals of the object. Seriously. Which it has almost free. And yeah, so this is the cloth. So we can take it out. Okay, then we should have what we have. The points. Okay. So these things here, it's meant to work with geometry. Okay. But geometry is made of what? Of points. Okay. So what happens if we use the same solver in a way which we are actually just taking care of the points and not the behavior among them? You can make points act as a rigid body with a closed solver, basically. Okay, so closed pop is analyzing what you throw at him, and if you do not put the attribute given from a basic geometry, so a grid and whatever, there's like point 1, 2, and 3 are making the primitive 1. Okay, so primitive 1 has those vertices. If those is not recognized inside of closed pop, it's basically telling you, my friend, no closed constraint. Input like a triangle, so triangle of something code that you can divide in more triangles. So basically it's telling you, but I will animate the point. Okay. So we are now animating some point, and the trick here is usually, I don't know, I'm thinking you are throwing this into spheres and then you want to have like bouncing here, so you can just throw a copy pop after and you're good to go. So bouncing something is something you would like to have from physics solver. Okay, it's also very good with this relaxation. It's very precise. So you see, at the end, after a while, everything should stop bouncing, more or less. You see, I'm very happy. And here basically you have this collision radius, which is should be how big are your spheres. If you make it this number, then you see that the sphere are not overlapping. If you make the sphere bigger, then they will of course expand. Here the collider, it's a floor with not so much friction. You see, we're passing through the sphere because the simulation not connected. This is another thing you will do in the Pro version as well. You can connect multiple clove pop in one solver. They slide, okay. So we don't want this to slide, so we encourage a bit more friction, very sticky. And yeah, then we have this. They stop after a while, and they are also exploding faster because we are putting the collision radius bigger. So in the beginning, which they are compacted like this, many of them will not have this collision radius enough big, so there will be an explosion due to interpenetration of pseudo radius in point. So you do this and boom, they explode, which is actually what we want. If you make this like tinier, very very tiny, it just fall down and then they behave as this bouncing entity. Okay, nice. Then we have what we have. We have the deformable. Okay, so this is a sphere which has. And here I also show you a limitation. Okay, here is simulating one object with a lot of constraints. Okay, like we have a lot of points that will result in dot vertices, and we are there is a lot of triangles. Okay, not so much, but a lot. Clove pop, since it has to solve all the constraints in one frame, maybe you get this effect of slowliness, let's say. Okay, so things that are going slow, even if you pretend they go faster. So where is the here? So gravity is 98, and it's still like going that is falling with not so much gravity. So even if then I put 100, then you back to something you would expect with normal gravity, maybe 70. Okay, so if one object has a lot of constraints, and this is a volumetrical object, because here we are using volumes. Okay, so in this example here, the box, the sphere, pardon, because we are trying to solve every of these triangles, so to keep it with a precise in a precise position in the sphere. And this can do how I'm doing the calculation, which is kind of normal in a XPBD system, this particle-based solver. Sometimes you can encounter this kind of slowness, so put more gravity basically. So if you want to go faster, do not use the speed, so at the end you won't do much. It will also increase the calculation time of the operator, and yes, you can increase gravity. Yeah, maybe here I should introduce you the sub-step and solver iteration. Okay, there is a computational way, so to basically overstretch or not in the calculation something. Okay, so the solver iteration, so we have a nested for loop basically. Okay? The solver iteration is doing two passes. So inside of this operator there is a feedback. Okay. This feedback is like going 2 times the bigger loop 2 times. Then inside of this we have sub-steps. Okay, so how many sub-steps? It's a nested for loop. Okay, how many sub-steps we need to do so to be happy for this step? So in 2 steps we have 4 iterations of the process of the solver, which is solving constraints. So basically we are repeating the things 8 times, more or less. There is a difference of behavior if you mix like 4 and you see it's becoming and 2. It's different, you see. You get a different behavior. Rispetto ai triangoli, actually. because now we are actually doing no, it's not this one for now. We're actually doing 4 times 2, and then the process is a tiny bit different. We have to play with this. This can become cookie. Okay, more time we repeat the process of taking those tiny triangles together. Yeah, can be hard. So play with this until you get something you like. More is become heavy computationally. Nice. This is the form of body. Yeah. Important things. We're not using volume. Why can you use a volume? Okay. You need something called the main folded geometry. Okay. So I explain it like this. You take a glass of water. You put water inside of the glass. If the water is not coming out, the glass is main folded. Okay. There is no way to escape from the glass. So the water stays inside. Basically, here we're doing the same. So this is another limitation of the free, because the other one can do some trickery, so to make folded geometry when you throw it at it. So you need main fold geometry. You won't explain much. So imagine a glass, you put the water inside of the glass, the water is not coming out, the geometry is main folded. So this sphere has no holes, basically. So if I don't put this, everything collapses. Okay, if I now turn it on, there will be a jump. Boing. And yeah, you will come back. Where is echo? Yay, nice. Okay, so now you see we're keeping the polymetrical structure, so we have more constraints to solve. I don't know how many it will build, but there are imaging some polygons also inside of the sphere, which are pretending to keep the shape. Okay. By doing this, you can actually achieve some inflation. So I can reduce this, and you get like something which is not keeping the shape anymore. So maybe you want to inflate it a tiny bit more. Boing, boing, boing. So now we went bigger than 1. Yeah, we have this. So we're even pushing air inside of 1 is like you keep the volume which is supposed to be 1. Then if you want to inflate it a bit more, then you have 1.4 Boeing. It started also to push from the outside, inflating this the form of body. Again, this you see if I make it very small, also change a bit the behavior. If I make it very big, very big, then it is helping a bit the stiffness. We don't need object. Okay. Play around with this. It's different. Okay. The formal body on a floor. Ta-da. Okay. Then we have this. Okay, here we have different type of geometries. So we have, let's see the scene first. So and some other attributes. Okay, so I have a very tiny sphere here, and it's also like stupid geometry. So it's not complex. It has 2 repetition, and it's a basic sphere. Okay, very choppy. Then I have some points, and I copy the sphere to the points until here. Easy, nice. Then I have a torus. Okay, here we have an attribute. So the cloud pop, the documentation, I hope to do it properly, can accept some attributes, and those attributes, one of these attributes for now is static. Okay, it means that it's a static object. It's not affected by um, it's not affected by the simulation. Okay, then I don't remember if this is picked on init or not. Let's see. Yeah, you can basically make init become a deformable and then put it back to a state where it was with one attribute. So now it's static, and then you make it become deformable, which is now collapsing inside of a grid. So here we can see actually some limitations. So we have to deal with reality, and basically, yeah, there are some imperfections which you need to deal with it. Anyway, having a parameter that you say you're static or not, it's nice. So take it. Okay, this is one of the most complex things because for the sphere I'm not even asking to keep the volume, and this is because, as I said, you need manifold geometry, and the grid is not 3D, so you can't hang some water. Actually, yes, you could, but not in this case. What you can hold, it's like some points, which is represented from those spheres here, which are pushing on the cloth. You can also go underneath this. See? Yeah. You see, you have. Yeah. The cloth is keeping the spheres, which is kind of good. This is also to showcase that here I'm having like C6 solver iteration to substep, and when I start the simulation there is not much interpenetration of object, at least from what it's supposed to keep them. Yeah. So you see there is a bit, but it's okay. I mean it's not 3D. It's very good. Okay, then if you don't know, you can use point pop to throw attribute inside of a field and output attribute, named attribute where you want, like painting attribute on a sphere, on a 3D object. And here we're actually using one very cool attribute which is pinned. Yeah, okay, so this is not black, it's gray, it should be a bit tiny bit more white, whatever, let's see it here. So go back here, take this field, and can I see with colors? No, doesn't see pinned. Yeah, maybe like this. Yeah, not very helpful, but here is pinned and here is not pinned. Okay, so this area is not pinned and this area is pinned. Nice. Touch design should work a bit more to make us see this. Maybe I can do what I can do. Can I do this? Oh, nice. Okay, this is no, very good. Okay, now you can always see where those points are. So when it's red is pinned and when it's blue no. And this is actually the behavior which we are throwing in the simulation. Ta-da, here. And the attribute pinned now it's here. You define pinned attribute, and the name is pinned, so what is being passed, named as pinned, then stay, basically. You can also say, you can stay how much it have to be based on the attribute. So here we are gradually holding the point. Another, by default, because this is meant to do like cloth easy, when you put a grid, So here I go back to this. Okay. So here we have the self-colliding cloth, and as you can see, I didn't put any attribute. Why? Because by default it's keeping the first line to help you check pin top row. If I take it out, this fall down. If I put it back, and it's coming back in a weird way, but it's nice. Okay, then it goes back to a state where it's kind of wavy but happy. Okay, that's it. It has been a long tutorial. This is Cloth Pop. Please enjoy, and if you can, drop a coin in my Patreon. Any contribution is more than welcome. Thank you very much.